7 kan. Okay. Okay. For this one, kita ada kosong campur. Ini berapa tadi? 3 kan? Okay, saya pun dah tak nampak dah.
3 doktor.
Kosong campur 3 and then sini akan jadi, okay, lupa buat ni. Okay, 3, so mari sini pun 3 campur 4 jadi 7. Okay, di sini 4, okay, 4 campur 4 jadi 8. Okay, so sekarang ni berapa untuk G? Early start untuk G.
7.
G dia dihubungi oleh E dengan D kan. So dia mesti menunggu E siap dulu. 7 adalah D siap. Tapi E belum siap. So paling awal G boleh mula adalah apabila E siap. Itu 8. 8 campur 3 adalah 13. So bilakah masa yang paling awal untuk this projek siap? Adalah 13 kan. Okay. Kita ambil yang paling besar. So G tak siap lagi kalau kita gunakan 7. Okay, jadi 13. Alright. So now try to look at the table given here. Okay. G 13. Okay, G dalam table ini ditunjukkan 13. Okay. Dalam table ini ditunjukkan 13. So apa yang maksud dengan table ini adalah early start dengan early finish. So jadi kalau kita tengok table ni 0, 2. Okay, we have 0, 2. 0 and 2. And then untuk B, kita ada 0 and 3. 0 and 3. Dan seterusnya, tapi yang terakhir adalah 8 dengan 13. Okay. Kita belum, ya 8 dengan 13 untuk G, yes. Kita dah ada. So now what we need to do adalah we go backward. Okay. Kita panggil backward pass. So in backward pass, kita mengambil masa untuk menentukan, okay, when is the late start. Late start equal to late finish minus the duration. Okay, the duration. Okay, so now we're going to have here, okay, so we have, sebab dia adalah kosong, sebab this just ending node. So 13, 13, semua jadi 13 lah. So di sini pun jadi 13, sini pun 13. 13 tolak 3 jadi 10. Okay, 13 tolak 8 jadi, 13 tolak 5 jadi 8. Okay, balik ke sini, dia akan jadi 8. 8 tolak 4 adalah 4. Okay, so balik ke sini adalah 8. 8 tolak 4 adalah 4. Okay, so di sini akan jadi, okay, sekarang jadi berapa sini untuk node C? C jadi berapa?
4.
Okay, kita ambil yang minimum. Kita ambil minimum. So sama ada dia 10 ataupun 4. So kita ambil 4. 4 tolak 2 adalah 2. Okay, sini jadi 2. 2 tolak 2 jadi kosong. Okay, di sini 4. Balik ke sini pun 4. 4 tolak 3 jadi 1. Alright, so sekarang ni kita dah mempunyai semua masa di mana telah direngkaskan dalam jadual ini. Okay, telah direngkaskan dalam jadual ini di mana kita dapat, okay, late start dengan late finish. Okay, jadi kalau kita tengok untuk activity A, okay, sama so kita kosong dengan 2. Kosong dan 2. Activity untuk B, 1 dan 4. Okay, 1 dan 4. Disenaraikan dalam jadual ini. Okay, so dan seterusnya untuk kesemuanya. Jadi kita ada satu kolom di mana slack. Slack ini adalah di mana kita membezakan antara, okay, sini kosong-kosong. Okay, kita tahu bahawa dalam node ini, okay, dalam node ini kita ada early start, late start. Early finish, late finish. Kalau kedua-dua masa ini, okay, let me get another highlighter color, different color. Okay. Kalau kita mempunyai, kenapa tak keluar? Okay. This highlighter is not working. Okay, tak apa. Just use a pen. Okay, maybe get yellow color. Okay, you nampak di sini Kalau these two number are the same, okay, maknanya dia no slack. Okay, if early start equal to late start, ni kita kata slack dia 0. Okay, dia tak ada slack, maknanya tak boleh lewat lah. Early start dengan late start sama. So you cannot delay, so is equal to 0. Begitu juga if, okay, if early finish, okay, sekiranya early finish, late finish minus early finish, kita ada beza. Okay, late finish, okay, late finish equal to early finish. So ini pun menunjukkan there is no slack, slacknya 0. Okay, jadi kalau kita menyemak jadual tadi, di manakah numbernya sama? Mempunyai number yang sama. Early start equal to late start. Early finish equal to late finish. Di node yang mana? Tanesh? Okay, can you respond to my question?
Node A,
Okay.
A, C, E, and G.
Okay, so we have A. They are the same, both number are the same. These are also same. And then lagi C. This
E.
also the same. And then
E,
E,
G.
G. Right? So
Yes.
this is what we call it critical path. Okay, critical path where there is no slack. Okay, dia tak boleh, maknanya no slack maknanya tak boleh delay. Tak boleh berlaku, tak ada masa tambahan, tak ada masa lebih. So it must go exactly as it is given in the network. Okay, so this is slack equal to 0. Okay, slack equal to 0 because both are the same. Early start, late start. Early finish, late finish. So this is also 0. This is also 0. This is also 0. So we call these are critical path. Critical path. Where is no delay is allowed for all activities on critical path. But activity F, activity B, activity E, there is a slack. Okay, there is a slack. Okay, so now what is slack? Slack equal to the difference between late start minus early start, or the difference between late finish minus early finish. Okay, Tanesh, I ask you again. Okay, activity F is not critical. This activity F is not critical. What is the slack for activity F?
3, sir.
This activity, right?
Yes, sir. 3.
3? How come 3?
7 minus 4, sir.
No. What is late start for activity? Let's say activity F. Okay, activity F,
Yes, sir.
What?
13 minus 10 is 3.
What? Activity F is
13
not
minus 10 is equals to 3, sir.
No. Where is the late start?
Late start is at 10, sir.
Late start is 10. Okay, early start? Early start
Early
is
start
here,
is at 4.
at 4. So what is the slack?
6, sir. Sorry, sir. My
6.
mistake.
Okay, slack 6, meaning that activity F, you can start either at 4 or at 10. Okay, there is no effect for to the completion time. You can delay starting of activity F by 6 days or six. What is the unit time here? I think okay, doesn't matter. It could be days or weeks, depend on the unit time. Okay, if you look at late finish, what is late finish for activity F? This activity. What is the late finish for activity
13.
13? Okay. What is the early finish? 7,
7.
right? So now it's going to be 6, right? So the slack is 6. Okay, you have the slack here is 6. Okay, as I put it on this one. Okay, slack here is 6. Okay, slack here. Is there any slack for B? Yes, right? 4 minus 3 and 1 minus 0, so it's 1. Is there any slack here? Yes, there's 1 slack. Okay, this one on critical path is 0 slack. So this is what is being shown in this table. Okay, so we have that. Okay, activity A, there is no slack. Okay, no slack here. Okay, because it is on critical path. This is also no slack. This one also no slack. No slack. Okay, but activity B and activity D and activity F, okay, which is B, D, and F, they are not on critical path. Okay, they are not on critical path. So we have a critical path with 0 slack. Okay, remember that critical path has 0 slack. Okay, critical path has 0 slack. So okay, let me erase this. Okay, so now you have a critical path which is shown by when there is no when there is no when there is no critical what do you call it, no slack. So okay, as shown here, the start A, C, E, G. Okay, A, C, E, G. Okay, this is the critical path. Okay, whoever being assigned to do this activity, he cannot do any delay. But those who are not in critical path, they can have a delay. How much delay depend on this. For example, this one can delay one unit time. Okay, on someone working on this one. Okay, sorry, someone working on this can delay 1. Working on this also 1. Okay, on F, it can have a delay for 6 days. Okay, 6 days. So if anyone being assigned A, C, E, and G, he cannot go for holiday. Okay, he has to complete his work first. All right. So any question on that? Any question? Okay, if no question, I'll give you a break for 5 minutes and we come back and I will discuss about variability in project time. Is it okay? Hello, everyone.
Okay, Doctor.
Okay,
Alright.
Doctor.
Okay. Take 5-minute breaks and then I continue with PERT. Okay, can we continue, please, everyone? Hello, are you there? Please respond.
Yes, sir. Yes, sir.
Okay, so everyone is back now, right? Okay, I'm sharing with you the PowerPoint. Do you see the PowerPoint? What do you see now?
Gantt chart.
Gantt chart. Okay, this Gantt chart is showing early start and early finish. Okay, for the Milwaukee paper example, with the green color. Okay, green color is showing early start, early finish. But if we plot, late start and late finish, it will looks like, okay, it will looks like, okay, like this, huh? Late start and late finish. Okay, so we see that there are activity which are not critical. Okay, activity not critical. If your starting point and ending point berbeza. Okay, for example, for activity B, you see activity B here. Okay, activity B. For this activity, okay, early start, okay, here 1 and then finish at this, at 3 here. Okay, kalau kita buat late start, okay, dia can delay kat sini one day, can start at 2, finish at end of 4 or 5, 5 is the beginning of 5, end of 5. So this is, we plot the difference. So when there is a difference there, maknanya ada kita panggil ada slack. Alright, so let me move on to the next topic, which is variability in activity time. Variability in activity time is referring to where we have many uncertainty. Okay, we have uncertainty in delivery of material. It could be uncertainty in time for completion of projects. Okay, so it's common in practice. Okay, there will be uncertainty. Okay, variability, maknanya uncertainty. There is many uncertainty. So the method that you have seen before, which is CPM, okay, critical path method, we assume the time is fixed. Okay, assume fixed time. For example, you say activity A, we need, for example, 3 days. So we are confirmed that it is going to be 3 days. But in reality, okay, in real life, nothing is fixed. Okay, nothing is fixed. It can be 3 days, it could be 4 days, it could be 2 days. Okay, so nothing is confirmed that is going to happen. Okay, sebab itulah kadang-kadang kita buat promise dan kita kata insya-Allah, okay, with the will of God, ya Allah, we are able to complete it. Because we are not sure. We are not sure that we are going to deliver it. But to the best of our ability, we try to keep it to our promise. Okay. Are we 100% sure? No, no one can make sure. No one sure about it. Okay, there is uncertainty. Okay, so we using PERT. Okay, what we call it, program evaluation and review techniques. Okay, PERT stands for program evaluation. Okay, somebody was asking. Okay, let me check again before this. Some program evaluation and review techniques. Okay, so these techniques, okay, these techniques, okay, these techniques is short form there, PERT, PERT. Okay, this technique consider probability distribution in the activity time. Okay, the activity time. So this allow us to have some flexibility, in the time estimate. I mean, in the completion time. So let's say we have activity, for example, we want to have to prepare. Let's say take one activity. Say we want to have delivery of raw material. Okay, kita beli barang daripada warehouse, daripada hardware store, nak deliver kepada construction site. So, okay, we are not sure, okay, how long that delivery. Okay, you could say, okay, it will be delivered within 7 days after we order. Kalau kita kata 7 days, itu adalah kita confirm bahawa it is a fixed time. But on PERT, okay, variability time, we have 3 time estimate. Okay, we have 3 time estimate. We have to know the 3 time estimate. Okay, what is this 3 time estimate? Okay, this 3 time estimate, we call it, okay, pessimistic time. We call it pessimistic, optimistic, and most likely time. Okay, most likely time. Okay. So this is what we have it here in the variability time. So we have optimistic time, pessimistic time, and most likely time. Okay, what is the meaning of this? Optimistic time is we assuming, okay, everything goes well. We are optimistic that we can say, let's say we estimate that the delivery time is 7 days. Okay, we are optimistic that nothing happened, no raining, no traffic jam, it can arrive from order to delivery is 7 days. Okay, but if we say that we are not sure, it could be traffic jam, it could be rainy days, and so on. Okay, pessimistic time will be, maybe we can say it could be 10 days. Okay, 10 days, pessimistic time. So we say A equal to 7, B equal to 10. Okay, how about most likely time? Okay, because most likely time maybe 8 days. Okay, 8 days. So 3 time estimate is given. So this is a method, what we call it, considering variability. Okay, variability. So when we have this optimistic, pessimistic, and most likely time, so we can calculate what we call it the variance. Okay, variance. Okay, so the variance will be B minus A divided by 6, okay, square root. Okay, variance is basically sorry, it's not square, it's square. Okay, the square root of variance is standard deviation. Okay, square root of variance is standard deviation. Right, so how can we use this in the project network? Okay, so we can use this in project network. Okay, so in order for us to estimate the time for each activity, okay, time for each activity is given by this. Okay, so estimated time, okay, TE or time estimate for each activity, is A plus 4M plus B. Okay, we divide by 6. Okay, this is the formula. So A is optimistic time plus 4 multiplied by most likely plus pessimistic time. So in the example that I give you earlier, okay, if we are optimistic time is, let's say, 7, okay, most likely time is 8, pessimistic time is 10, okay, we divide by 6. Okay, can somebody calculate for me what will be expected time for that delivery of something that you order from hardware store will arrive? What is the expected time in this example?
8.17.
8.17. Okay, 8.2. Correct. Okay. So instead of saying that it's going to be delivered in 7 days, you say, okay, 8.2, considering the variability. Okay, this one is actually following what we call it beta distribution. Okay, beta distribution. Beta distribution, where we have most likely will be here. Okay, optimistic will be here, and pessimistic will be here, the B. So we see actually very big bigger difference compared to between M and B compared to A and M. Okay, so following beta distribution. In terms of distribution, it follow beta. Beta distribution. Okay. So this is the only difference between PERT and CPM. Okay. CPM does not consider variability, the time is fixed. But when we have PERT, okay, we are considering the time is variables. Okay, this is what I was showing just now. You have optimistic time, most likely time, and pessimistic time. All right. So if you are given, you need to have a time estimate in this case. Okay. So let's see the example here. Okay. Let's see the example here. Activity A, you have optimistic time, most likely time, and pessimistic time. Okay. So 3 time estimate must be given. Expected time is using the formula that I've just shown just now, and this is the variance. Okay. So in this example, for A, how can you get 2? Just using the simple formula there. Maknanya untuk T estimated for A will be 1 plus 4 multiplied by 2, okay, plus 3 divided by 6. Okay, you're going to get 2. Okay, so the variance here, okay, the variance is, okay, the largest, which is 3. Okay, 3 minus the smallest, which is 1, divided by 6 and square that. So we do all for all the activities. Okay, all the activities. All right. From there, we move on. Okay, we move on from there. Okay. Okay, why it's not moving? Okay, it's annotation. Okay, I don't want to do annotation. Okay, let's move on. Okay. Okay, so if we want to calculate the completion time, we have to know the variance for the projects. Okay, variance for the projects is related to activities on critical path. Okay, we have to make summation of project variance on critical path. Okay, project variance on critical path. Okay, so this is variance. Sigma square is actually project variance. Okay, P meaning that is for projects. So what we got is we have to find only variance on critical path. Only critical activities are is used. Okay, is used in the calculation of project variance. Okay, so okay, let's show this on the example. Okay, let's show this on the example. Okay, so in the previous example, only activity related to critical path are used. Okay, are used for the purpose of this. So and finally, we get a variance for the project is 1.76. Okay, all right. Okay, so this is normal distribution. The distribution for completion project completion time follow normal distribution. Okay, it will follow normal distribution, and okay, in this normal distribution, we see that what we have seen like in the topic on quality, topic on quality, you have normal distribution. So the expected completion time was 15. This example is using the same example for Milwaukee papers, and then the standard deviation was calculated based on the variance of critical activities, 1.76. Okay. So now if we want to know what is the probability of completion, okay, for this project, which is completion time of T equal to 15 weeks. Okay, actually only 0.5. Okay, only 0.5. Why? Because 15 is in the middle here. Okay, so this project will be completed 50%. We are confident, only 50% confident. Okay, we say 50-50. I can complete this project within 15 weeks. Within 50 weeks. Okay, let's say the customer would like to know, okay, can you estimate when is the project can be completed in, let's say I want it 90% confidence. I don't want 50-50. I want 90% confidence. Okay, so we have to find what is the value here of the weeks. Okay, what is the value of weeks? Okay, the new T here. Okay, where you get 90% of the area covered. Okay, this is same as looking in normalized, standardized normal in quality. Yeah? So we want it 90%. So what will be the Z value? Okay, what is the Z value here? Okay, the Z value of that. Okay, so this requires us to use again the standardized normal table. What is the Z for 90%? Okay, so the formula that we're going to use is almost the same as what we use in quality. Okay, in quality, we have, okay, in quality we have, okay, we have used the same Z, Z formula, normalized, standardized normal. Okay, standard normal, where Z here in quality, you see that Z equal to X minus mu, okay, X minus mu divided by sigma. Okay, so in this case, sigma will be sigma P, sigma P, and X will be the due date, okay, the due date, which is the T, and expected completion time will be the mu, okay, the mu. Okay, in our example here, the mu was 15, okay. So if you want to know what is probability of completing this project within 16 weeks, we just put it 16 minus 15 divided by sigma. So 16 weeks, the probability of completion is 57%. So my question was, when is this project can be completed with 90%? Okay, I would like you to try, okay, to tell me when is the project can be completed in 90%. Okay, when project can be completed, okay, project can be completed okay, with 90% confidence. Okay, can you try? And you need to look at standardized normal table, which is at the end of your ebooks. There is a table there. Okay, please, everyone look into it. Okay, I will ask you randomly. Okay, when is the completion, estimated completion time for the project? Okay, having mu equal to 15, okay, sigma equal to 1.76. But I want it not 57%, I want it 90%. When is going to be completed? Okay, can I have the answer? Anyone, please? Any volunteer? Okay, Ruzaidi Zikri. Okay, what is your answer? No answer? Okay, you can put in the chat box if you cannot speak. Okay, anyone please can put it in the chat box. What is the answer? Nur Fazira. Okay, you can the answer? Okay, Jihan Rosman, you have the answer? Okay, can I ask Khairul Amirin? Okay, what is the Z value for 90%? Hello? Okay, this is the normalized table. Huh? What is the Z value for 90%?
Not sure, Doctor. Still finding the appendix.
Okay, do you see my screen now?
Yes.
Okay, can you? Okay, this is appendix 1. Nampak appendix 1. So now my question was, okay, where is the value when we have in this normalized standardized normal, you have 0 in the middle. Okay, so the extreme value in this table will be more than 3, minus 3. Same what we learned in quality. This one is also 3. If you look at this table, Z value Okay, the last number here is 3.9. Okay, 3.9, and this is 9999. So this is almost 1 lah, almost 1.0. So meaning that it covers the all of the area under the curve. So my question was, I want it 90%. Okay, I want it 90% that we are sure that the project is going to cover. So meaning that in this one, so this curve, okay, to the left of this line, okay, which is this is Z value. This is Z value. Okay, these are the Z value. So where is the value for Z covering, representing the coverage of 90%? So I just want to get that value. Okay, can you see from this table?
Uh, 1.3, sir. Is it 1.3?
1.3.
3.
We have 1.3. 3 what? 1.3 is here. Okay.
1. I think 1.29.
Okay. So it is 1.29. Between 1.29 and
1.3 or 1.28.
1.28. Okay. Between 1.28 to 1.29. Okay. If you do interpolation, the value will be between this. Okay. So this is the Z, the value for Z. Okay. The value for Z. Okay. So it will be, which one is closer? Okay, somewhere here in between. Okay. If I'm not mistaken, it will be to 1.282, 2.82 or something like that. Okay, let's say we just, okay, we want to get accurate, we have to do interpolation, but if the time is not sufficient, we just assume that, okay, any number between these, any number. Let's say for the sake of simplicity, okay, I will say, okay, because this one is 90, this is 2, okay, it's actually closer to this one. Closer to this one compared to this one. Okay, so let's say 1.28. Okay, so for 90%, okay, my Z will be 1.28. Okay, 1.28. So now back to my original question. Okay, I want to know. Okay, I want to know when the project will be completed. Okay, can you use this number in the Z formula that I just shown to you earlier? Okay, everyone, please try. So using this formula, Z equal to X minus mu divided by sigma. Okay, so in our case, Z will be, X will become the T, which is we want it 16, okay, minus the mu, which was given as 15, and the sigma was 1.7. 7 what tadi? 76 or 78? It's 76, right? Can anyone confirm to me the value for sigma? Yes, 1.76.
Yes.
Okay. So what will be the T? Which is what we are 90% confident that this project will be completed within, okay, 90% confidence.
17 weeks, sir.
17 weeks, okay? 17.2 something, so 0.3, right? I think.
Yes.
Okay, so we can say that we are confident that this project will be completed, okay, 90% confident, 17.3. If the owner say, no, I want it 100% sure, how many weeks will it completed? Okay, he said, no, I don't want 90%. I want it 100% sure. Okay, with the will of Allah. Okay, I want it 100% sure. Okay, how many days, how many weeks of this project should be completed?
22 weeks, sir.
22 weeks. Okay, so we just get the Z for 3.999, which is very close to 100% coverage of the area. So you get it just now. It was 22 weeks. Okay, 22 weeks. Okay, so you see that 22 weeks. Okay, we can say inshallah 100% finish. Okay, but if you say 15 weeks, okay, as in the original question, we can say I can guarantee you inshallah 50% only, 50-50. Okay, the completion time. So now you understand the use of variability in project management, estimation time. Okay, so I hope that is clarify this issue of variability. Yeah. Okay, let me sharing with you again the slide. Okay, stop sharing there. Okay, let me put the PowerPoint. Okay, you see the PowerPoint now, right? Okay. Okay, so we use this formula for variability. So, okay, you now know how to read the tables. Okay, know how to calculate the completion time with a given probability. Okay, so okay, there is also important to know the variability of non-critical. There are times where high variability in non-critical activities may change the critical path. Okay, variability time on activities on non-critical must be considered when finding probability finishing in a specified time. Okay, variation in non-critical activity may cause change in critical path, especially when variability of non-critical activity is very high. You need to calculate the to check whether critical path is changed or not as a result of high variability in non-critical activities. Non-critical activities may have high variability that finally your critical path is changed due to that non-critical activities. So that one is you can what? Okay, let me show you example here from your e-books. Okay, you see the e-books now? Hello?
Yes, sir. Yes.
Okay, so as I said just now, okay, the variability of non-critical activities may change your critical path. Okay, may change your critical path. This might happen. Okay, this might happen. Okay, I show you example here from your e-books. Okay, on chapter 3. Okay, on chapter 3. Okay, 320. Okay, okay, later on you will look into this. Okay, let's say this estimated time. I'm referring to 320, question number 320, estimated time given here for 4 activities and predecessor and activity estimated time based on optimistic, most likely, and pessimistic. Okay, assume the critical activity are independent. And in the last question here, 3.D, number D, explain why probability that the critical path will be finished in 22 weeks or less is not necessarily the probability that the project will be finished in 22 weeks or less. Okay, so this might happen when the variability or the variance of activity is very high. It may change the critical path. Okay, so we need to check actually the variability, the variance of each of activity, especially when the variance is very high. Okay, it will affect critical path. Okay, if we have example here, okay, let me share with you. Okay, if we see here, okay, the variance, which activity has high variance in this among A, B, C, D, E, and F? Which one have high variance?
FG.
Okay, activity G is very high, right? Very high variance. So we have to check, okay, whether these are on critical path or not, F and G. Okay, F and G. Okay, so because it may affect the completion time. Okay, in the completion time. So we have to check whether this affect or not. Okay, so in this example, I think it's not mentioned. Where is the critical path? Okay, activity 1.78. But anyway, if we have to check if it's already on critical path, is fine. If it's not in critical path, we have to check non-critical path. Okay, non-critical path, whether this will affect or not the completion time. Because in our formula, okay, in our formula that for the probability of completion, we have this value of T minus mu divided of this. So this one, okay, this value, okay, influence this T, which is T equal in this case is, okay, T equal to Z sigma plus mu. Okay, if this T is high, okay, so this value is going to be high also. Okay, so it's not enough just looking at sigma P. Okay, so we also need to look into also non-critical. Okay, but in general, okay, sigma P here is used, okay, when there is a normal situation and variance of non-critical is not too high. Okay, so that is very important note that you have to be careful in finding the completion time, okay, when there is variability. Okay, let me highlight this aspect of the next aspect of project management is related to, okay, what we call it project crashing. Okay, project crashing is when there is, okay, this is another aspect. We finish about the project variability. Now another aspect of project management is we call it cost and time trade-off, or we call it project crashing. Okay, why project crashing is important? It is important when we want to reduce the completion time. Okay, to reduce project completion time. Okay, let's say the example just now, it was given as 15 weeks. Okay, suddenly the owner of the project said, no, I don't want 15 weeks, I want it 13 weeks. Okay, so he give you the deadline. Okay, based on our calculation, it was 15 weeks, but he said, no, I don't want 15 weeks, I want 13 weeks. So what you do, this is what we call it project crashing. We have to crash, okay, from 15 weeks to 13 weeks while reducing 2 weeks reduce. How this can be done? Of course, it will increase the cost. Okay, cost will increase. Okay, you want it faster, you have to pay additional cost. So this is leading to the need for us to find the crash cost. Okay, so the crash cost is given by this one. Okay, so where we have crash cost minus normal cost divided by normal time to crash cost. So this is crash cost period. So another way is we call it slope. We got a slope. Okay, so the slope of the cost, okay, crash cost, okay, which is the cost during the crash, okay, minus the cost that you get it from the normal, divided by time, okay, the time which is we call it normal time. Okay, normal time. If I may use t as a time for the normal, minus time for crash. Okay, so this will be the slope. Okay, the slope for the cost per period. Okay, so if we put this in terms of graphic, we will looks like this. Okay, so we have time, we have the cost. Yeah, okay, we have the cost. So this is crash time, which is shorter than normal time, and we have normal cost, which is lower than crash cost. Okay, so this is the slope that we call it the slope. Just not the slope of that. So in order to solve crash cost, we need to find the slope for all the activities. Okay, you need to find the slope for all activities, which is shown here in this example. You have activity, you have the time, normal time, crash time, cost, normal cost, and crash cost. And this is the slope. Okay, this is the slope. Okay, after having all this, okay, we need to identify which slope are on the critical path. We already know which critical path. Okay, A was critical path, C was critical path. Okay, from the earlier information, we know already this critical path. Okay, so if you want to crash only critical activity. Crash only critical activities. Okay, and second rule is, okay, priority to crash. Okay, because we have many option here. A is critical, C critical, E also critical, and F critical, G critical. So we give priority to smallest slope. Because why? Is the cheapest. Okay, crash cost per week, the cheapest is, in this case, it will be not this one, it's not critical, it will be this one. And the third rule is crash one by one. Okay, meaning only one period at a time. Okay, any question to that up to that point? Hello, any question? You can ask any question. Is there any question? Respond to chat.
No, doctor.
All
Clear.
right. Okay, I would like you to go through this, okay, example for you to understand how the crashing can be done. For example, here you have 15, okay, if you want to reduce it to 14, okay, from 15, we need to crash, become it 14. From 14, we further crash it to 13 if you want it 13 weeks. Okay, must do it one by one. You cannot crash directly from 15 to 13. Cannot. Okay, why? Because every time you crash, the costs are different. Okay, because we have different slope. Okay, every time you crash, you might change the critical path. Okay, because this unit of crashing is per week, per one duration period, at one period. So when you crash, after you crash, and let's say you have selected just now in the example of this, the cheapest one is A. The normal time is 2, crash time is 1, meaning that you can crash only 1 week. Activity A can be done using 1 week at the cost of 22,750. But if you use it 2 weeks, the cost is $22,000. Okay, additional $750 if you make it shorter 1 week. Okay, so what is the cost of this project? Is summation of all these costs. Okay, summation of this cost is the cost for the project. So, but if you crash it 1 week, the cost will additional, okay, of whatever you have that, you have to add 750 additional cost. Okay, after you crash that from 15 become 14, you have to recalculate the critical path again. So this one, if you crash A will become 1 here. Okay, the rest is the same. So you need to calculate again. And this one will become, most likely will become 14 lah. Okay, so dia become, di sini akan jadi 1, di sini akan jadi 1. Okay, kena redo the whole critical path calculation until you get here is 14. Okay, here is 14. Here I think is, okay, still, so it's become 12. Something like that, okay? So you have to check the whole network with a new critical path, and after that check again when is the slowest, the smallest slope, and then you crash that again and then redo the critical path. Right, so I think that's all. I think time is up now. Thank you very much for your attention and participation in this class. Okay, remember next class, at the beginning of next class, we give you a quiz on quality. Okay, so the class will start at 12, we finish at 1 because I have another activity, official activity in the school, okay, on that day. Okay, is it okay? We start at 12 on Wednesday.
Boleh, doctor.
All right, thank you very much. Okay, Assalamualaikum warahmatullahi wabarakatuh.
Doctor.
Sama.